Suppose we have a triangle, and on each side I've chosen one blue point. The question is, how do I choose these 3 points so that I ensure that this line, and this line intersect at one point? Or, if I know that these 3 lines intersect at one point, what's the relationship between these ratios here that I chose when constructing the 3 blue points? Ceva's theorem gives us an answer to these questions. Let me label this length as A, this B, this C, this D, this E, and this F. Then Ceva's theorem tells us that A divided by B times C divided by D times E divided by F equals 1, if and only if these 3 lines intersect at one point. Here's how you might remember this statement. You color the vertices of the triangle in black and the points on the side of the triangle in blue. Each blue point corresponds to division, and each black point corresponds to multiplication. We start at one of the vertices of the triangle, and we get A divided by B times C divided by D times E divided by F, and then we come back from where we started, which means that the result must equal 1. This is of course only true if we know that the 3 red lines intersect at one point. Now let's prove Ceva's theorem. Suppose first that we know that these 3 segments intersect at one point. Let the area of this triangle be S1. Let the area of this triangle be S2. And let the area of this triangle be S3. We know that A divided by B equals S3 divided by S2. We know that C divided by D is the area S1 divided by the area S3. And we know that E divided by F is the area S2 divided by the area S1. And so we can rewrite this expression as S3 divided by S2 times S1 divided by S3 times S2 divided by S1 equals 1, which is obviously true because S1 cancels here, S2 cancels here, and S3 cancels here. Therefore, if these 3 lines intersect at one point, then this equality holds. Now, let's suppose that we know that this equality holds. Let's prove that this line, and this line intersect at one point. Here you can see that they don't intersect at one point. And I constructed this line for which, if we take this point instead of this point, then this point, and this point are such that these 3 lines intersect at one point. I'm going to prove that this green line and this red line coincide. We know that this distance is A and this distance is B. Now I'm going to denote this distance by A prime and this distance by B prime. Now, using this green point, I know that this, and this intersect at one point, and therefore this equality holds. Now that I have these 2 equalities, I can divide one by the other and get A divided by B times B prime divided by A prime equals 1, because C and D would cancel out and E and F would also cancel out. And this can be rewritten as A divided by B equals A prime divided by B prime. Now I can add 1 to both sides, and I get A plus B divided by B equals A prime plus B prime divided by B prime. But A plus B equals the length of this segment, and A prime plus B prime is this plus this. It is the length of the same segment. And so we can cancel out A plus B with A prime plus B prime, and hence B equals B prime, which means that the green point coincides with the blue point, and therefore the 3 red segments must intersect at one point. It's good to know that there is a second version of Ceva's theorem. Suppose this is our triangle, and then one of the points lies on the side of the triangle, but the other 2 points are external to the sides of the triangle. This line, and this line intersect at one point if and only if A divided by B times C divided by D times E divided by F equals 1. You can use the same mnemonic to remember this. It is A divided by B times C divided by D times E divided by F equals 1, where the blue points have division and the black points have multiplication. And the black points are just the vertices of our triangle, while the blue points are the ones that are chosen on the sides of the triangle or on the extension of the sides. For the proof, we need to consider the following areas. Let S1 be this area, let S2 be this area, and let S3 be this area. Then S1 divided by S3 is this divided by this, which is C divided by D. Now let's try to prove that S3 divided by S2 equals A divided by B. Well, the area of S3 is this base times this height divided by 2. And the area of S2 is the same base times this height divided by 2. And so the ratio between this area, S3, and this area, S2, would be equal to the ratio between this height and this height, because the two triangles have a common base, which would cancel out, and the 2's would also cancel out. Notice that this green height is parallel to this green height, because this angle is 90 and it equals this angle, which is also 90. And therefore, we can apply the intercept theorem for this triangle with this parallel line. It follows that the ratio between this height and this height is exactly the same as the ratio A divided by B. And therefore, S3 divided by S2 equals this length divided by this length equals A divided by B. And similarly, the area S2 divided by the area S1 we can find equals E divided by F. And now this equality obviously holds because this cancels out here, and this here, and therefore this equality must hold. As we did before, when all the three blue points were internal for the sides of the triangle, we can prove the reverse direction, that if we know that this equality holds, then we know that these three red lines intersect at one point. This is the optional problem. We have three circles, each of which is external for the other two, and all the inner common tangent lines are drawn with respect to each pair of circles. For example, for this circle and this circle, this is a common inner tangent line because it's tangent to this circle at this point and to this circle at this point, and the two circles lie on opposite sides of this line. One lies on this side and the other lies on this side. Similarly, we construct this common inner common tangent line to the two circles, and then this one, and then this one, and this one, and this one. These points here are the intersection points of the three pairs of inner common tangent lines with respect to each pair of circles. For example, this point is the intersection point of the two inner common tangent lines with respect to this circle and this circle. We need to prove that if these are the centers of the three circles, then this line, and this line intersect at one point. And here's the solution. I'm going to show that this point, and this point lie on a straight line. We'll consider this point. We have two tangent lines drawn through this point to this circle, and this is the line that connects this point with the center of the circle. Therefore, this here is an angle bisector of this angle, so this angle equals this angle. Similarly, this line is an angle bisector of this angle, and so this angle equals this angle. And now, since this is a straight line and this is a straight line, we know that this whole angle equals this whole angle, and so the half angles on both sides are equal. This means that if this angle is 180, then this angle here is also 180, meaning that this point, and this point lie on a straight line. Similarly, we can prove that this point, and this point lie on a straight line, and this point, and this point lie on a straight line. Well, now we have a triangle and 3 points, one on each side of the triangle, and we're wondering if this, and this intersect at one point. So we can apply Ceva's theorem. What do we need for applying Ceva's theorem? We need the ratio of this length to this length. Let's see, if this is the tangency point and this is the tangency point, we have that this is 90 degrees and this is 90 degrees. And so we can apply the intercept theorem because this line is parallel to this line because of the two right angles. And so this divided by this equals this radius divided by this radius. Let's call this radius R1, this radius R2, and this radius R3. Then we know that this divided by this is R1 divided by R2. And similarly, we can show that this divided by this is R2 divided by R3, and this divided by this is R3 divided by R1. And so the desired ratio for Ceva's theorem, this divided by this times this divided by this times this divided by this, is equivalent to R1 divided by R2 times R2 divided by R3 times R3 divided by R1. But as you can see, R1 cancels with R1, R2 cancels with R2, and R3 cancels with R3. And so the whole expression equals 1. And therefore, from Ceva's theorem, we can conclude that the three lines intersect at one point.